When this load is lifted at constant velocity or is just suspended, then it is in the state of equilibrium. And equilibrium is what we're going to study in statics. So in this chapter, we will study equilibrium of a particle and show how these ideas can be used to calculate the forces in cables used to hold suspended loads like this. Today, we're going to introduce the concept of a free body diagram, FBD, and show how to solve particle equilibrium problems using equation of equilibrium. First, review the terms or idealizations. First, we say we're going to do equilibrium of a particle. So what is a particle? A particle is an object that can be modeled when its geometry or dimension are negligible for the interest of the study. So we mentioned in the introduction that a particle is considered to only occupy a single point in space with no shape or size, and it has no properties except for its mass. So we do need to consider the mass of a particle, but not the size. Everything will be reduced to a single point, even if it's a big object. But when compared to the problem we are solving, the size and shape is not important. For example, when we do research or when we study the Earth, how does it orbit around the sun, then the size is not important to the problem of interest. Then we can simplify it or idealize it as a point. A particle is said to be in equilibrium if it remains at rest if originally at rest, or has a constant velocity if originally in motion. This should remind you the Newton's first law. So, to remain equilibrium, that means this particle must satisfy Newton's first law of motion, which requires the resultant force acting on the particle to be equal to zero. And this condition is stated by the equation of equilibrium. The vector sum of all the forces acting on the particle is zero, then the particle is in equilibrium. Some examples that we can apply particle equilibrium to solve problems. So there's one example. If we want to know the forces in that strap, we can use the particle equilibrium or equilibrium of a particle to solve the problem. Or in this example, similar, we can solve the forces in the cables AB and AC using particle equilibrium. Or in this example, we have one given force applied at cable AB or BA, and then we can find the force developed in cable BD and BC using particle equilibrium equations or equilibrium of particle, and then further calculate the size of the cable based on the given material property of cable BD and BC. We'll start with 2D problems or coplanar force systems, which means the forces lying on a sheet of paper or lines within a plane. Well, basically, it's just a 2D problem. We have x and y coordinates. There's no z dimension or third dimension. So this is one typical example you're going to get for a 2D equilibrium problem. And usually you will have one force given, or in this example, we have the weight given here. And we will be looking for the force or forces developed within the cable AD and AB. So let's clarify one thing. If the whole assembly is in equilibrium, then particle A is also in equilibrium. But basically, if the whole assembly is in equilibrium, then any point, any part of the system is also in equilibrium. And to solve this kind of problem, or to determine the tension in cables for a given weight of cylinder, we need to learn how to draw a free body diagram and to apply the equilibriums of equations of equilibrium. In fact, those are the two major steps that we're going to apply throughout the whole course. Two major steps to solve an equilibrium problem. First, draw the free body diagram. Second, apply the equations of equilibrium to the free body diagram, and then solve for the unknowns. Now the question is, what is the free body diagram? Free body diagrams are one of the most important things for you to know for statics and mechanics of materials and dynamics and other subjects. So let's see what is the free body diagram and why do we use it and how do we do it. Free body diagram, first of all, is a drawing that shows all the external forces acting on the particle or on the body. And why is it called free? Because the particle is isolated and free from its surrounding. And why do we use free body diagram? Because it is the key to being able to write the equations of equilibrium, which are used to solve for the unknowns. Let's use this example to show how to draw a free body diagram. So the first step is to identify the problem. Let's say we're going to draw the free body diagram of point A. Now the second step is to isolate the object and simplify it to a particle. So let's say this is the particle A. Step 3, establish the x and y axis in any suitable orientation with point A as the origin. In most cases, the orientation of xy axis will look like this, horizontally and vertically, but in some other cases you will see later, it can be any orientation. As long as x and y are perpendicular to each other, then you can solve the problem. Step 4, show all the external forces that act on the particle. So remember, we're looking at external forces, not internal forces. But when we isolate the point A, then everything else becomes the external of this point. So think about if we do an imaginary cut or just remove this point A from its surrounding, but we're going to remove all of the cables, but we're only going to leave the forces exerted by those cables on this point A. So first we can see this case cable DA or AD, right? So there will be a force exerted on particle A by AD, cable AD along the AD direction. So we can call it FD since everything's starting from the point A. So to make it simple, we call this force FD. Since I do not know the value yet, I just put the symbol here for FD. Similarly, we have cable AB. There's a 30 angle degree between the AB and the x-axis, so the AB force will pointing up with a 30-degree angle. You want to put a 30-degree angle here on your free body diagram because you will need that value to write your equilibrium equations. And this force is also unknown. We'll call it FB, pointing from point A to point B. And there is one more cable that attaches the weight down here. So this, we can call it a force AC or force C, but this value actually is already known. We can give it a name or we can just write down the value here directly. 40, remember 40 is the kilogram, which is the mass of this weight or of the cylinder. So you have to calculate the weight here. Remember, we're using forces here, not the mass here. So times, let's do 9.82 gravitational acceleration. Well, let's put units for those quantities so we don't make mistakes. Step 5, identify each force and show all known magnitudes and directions. Show all the unknown magnitudes or directions as variables. Actually, we already did this while we're doing step 4 to show all the external forces. So here, 40 times 9.82, that's the known magnitude and direction. That's one given force. For the other two, force FD and FB along the cable AD and AB, we don't know them yet, and we're looking for them. Therefore, we just put the variables, give them a name, and place the direction and those variable, the names of the forces on the free body diagram. And we're done. And now this is the free body diagram of particle A. After we have this free body diagram at particle A, we can start the second step, which is to write down the equations of equilibrium. Since particle A is in equilibrium, then the net force at A is 0. So we have three forces exerting on particle A, FB, FC, and FD. So the resultant of the three forces should be 0 to make A in equilibrium. Now, in general, for a particle in equilibrium, this is the equation we are going to use. So for a vector to be 0, since we said this is the net resultant vector force, for a vector to be 0, all the components should be 0, meaning the sum of x, or sum of forces in x direction, and the sum of the forces in y directions both need to be 0 to have a 0 vector. So this equation is called a vector equation or vector approach. We use the vector formulation to get the resultant vector, and we make all the components equal to 0 to solve the unknown forces. But for 2D, we can also use the scalar approach, which is very similar to the vector approach, just that we don't need to use the I hat and j hat term. Instead, we collect all of the forces in the x direction, and it should be 0. We collect all the forces pointing to the y direction. This is also equal to 0. So that means in a 2D problem, we can write one vector equation, or we can write two scalar equations. And both of those equations can solve up to two unknowns. Let's do the second step. Write the equations of equilibrium. Before we can write the equation of equilibrium, usually we need to resolve the force into x and y component. So since FD and this given force are pointing either to x or y direction directly, so we don't have to resolve those two. So we need to resolve FB into x and y component. Can drop a perpendicular line from the head of FB to the x-axis, and this is the FBX. Same idea. Drop a perpendicular line to the y-axis, and between the origin and the point here, this is FBY. And then we're going to use trigonometry to figure out the relation between FBX, FB, and FBY, FB. So FBX equal to FB times cosine 30. Okay, it should be cosine 30 degree. And FBY is FB sine 30. Now we can write down the equations. Keep in mind that for 2D particle equilibrium problem, we can write down two independent equations. Sum of fx equal to 0 and sum of fy equal to 0. And sometimes you can specify the positive direction of those components by putting positive notation. So for x components, pointing to the right means is a positive value. And for the y component, pointing up is the positive direction. And this is actually also shown on our XY coordinate system or on the free body diagram. So now we can write the values into each equation. In the x direction, we have two forces. One is FD, which points to the negative x direction. So we'll put negative FD here. And the next component will be FBX, and FBX points to the positive x direction. So it becomes a positive value, and it's FB times cosine 30 and equal to 0. And for the second equation, we also have two components. One is the FBY, which points up or positive value. So we'll have FB times sine 30 degree minus, because the weight is a force pointing to the negative y direction, 40 times 9.82 Newton, because kilogram meter per second squared is Newton. This equal to 0. Check our equations to see, do we have enough equations to solve all of our unknowns? So we have one unknown FD, another unknown FB, and well, we have two unknowns, right? This is FB as well. So FB and FD are two unknowns. You have two equations, we can solve two unknowns. And after solving those two equations, here is the answer. FB is 785 Newton and FD is 680 Newton. Let's see another example. So we're given a box weighs 550 pound force. So please keep in mind that on this textbook when you see pound, it means it's pound force. So is the US customary unit system for force. So it's not a mass unit for pound mass, but it's for pound force. So we're going to use pound force for all of our solutions, and we don't have to convert mass to weight. And the geometry is as shown in this figure. The forces in the ropes AB and AC are to be found. So we're going to take the two steps. The first step is to draw the free body diagram at particle A, since we're looking for AB and AC, which both starting from A or attached to A. And then we're going to apply the equations of equilibrium to solve for the forces in AB and AC. So this is the given force and the geometry. And we're looking for FB and FC. To solve it, we're going to take the two steps. First, free body diagram at A. We're going to isolate point A and build XY coordinates. Then we're going to show all of the external forces with their magnitude and orientation, or with their name and orientation if we do not know the magnitude yet. So first, for the force FB, from point A to point B, we don't know it. So this is FB and 30 degree angle. And next, FC, directed from point A to point C, we also don't know the magnitude of it. and there is a slope triangle. We need to place it on the free body diagram because we need to resolve FC into X and Y component, so we will need this slope triangle. The next one is the weight of this box, which is 550 pound force. And this will be the free body diagram of A. Let me take one step further to resolve FC into X and Y component. That way it will be easier for us to write down the free body, to write down the equations. So this is the FCX, and use this slope triangle. FCX is 4/5 times FC, and FCY will be 3/5 times C. And don't forget the direction of the forces. Second step is to write the equilibrium equations, or equations of equilibrium. So we have two equations. One is the sum of Fx equals 0, and the next one is sum of Fy equal to 0. Okay, seems like I forgot to resolve force FB into X and Y component, but we can eyeball it, right? Since you already did so many of this kind of problem before, so let's just do the eyeball. First, for the FBX, well, it will pointing to the negative X direction, will be negative FB cosine 30, because it's pointing to the negative X direction. And the next X force will be positive FCX, which will be 4/5 times FC. And these are the only two forces pointing in the X direction. So equals to 0. And same idea for the Y components. We have three Y components. The FB of Y, FC of Y, and also this 550 pound force pointing down. So don't forget this force, the given force. So FBY is pointing up, so it's positive Y direction. It will be FB sine 30 plus 3/5 FC minus 550 equals to 0. Double check number of unknowns. We have FC, FB, so two equations, two unknowns. We solve them. We can solve both FCM and FB. And here are my answers. Three types of supports often encountered in particle equilibrium problems. The first type of support is simple springs. So if we have a spring in the problem, then the force exerted by the spring is calculated by using the spring constant multiplied by the deformation of spring. So the deformation of the spring means the elongation of the spring. So the elongation, or the change in the length of the spring, equals to the final length, the length after a force is exerted, or we use a force to pull on the spring. L, that's the final length. Subtract the initial length. The initial length is when there's no force applied on the spring. That's the length. So the length, the change in length is the final length, subtract the initial length, and that is the deformation of the spring. So the force exerted by the spring equals to K, which is the spring constant, times deformation, L minus L naught. The second type of support is called cables and pulleys, shown in this figure. Keep in mind, first, cable can support only a tension or pulling force, because the cable is soft. It cannot push on the subject. And this force always acts in the direction of the cable. So in this case, we have two tension or pulling forces, T1, which is pull in this direction, and T2, pull down. And second, the tension force developed in a continuous cable, which passes over a frictionless pulley, must have a constant magnitude to keep the cable in equilibrium. So this is the cable passes over the pulley, and we have just one cable. So for this cable to be in equilibrium, the tension force inside of this cable is the same anywhere along the cable. Because of that, we will have this relation. With a frictionless pulley and cable, T1 equals to T2. So the force developed in a continuous cable has the same magnitude everywhere and is a tension or a pulling force. The third type of contact or support is called smooth contact. So let's take a look at this cylinder, which rests on a smooth surface. It's inclined surface with 30-degree angle with the horizontal ground. And if an object rests on a smooth surface, then the surface will exert a force on the object. And this force is normal to the surface at the point of contact. So one thing to keep in mind is in this kind of contact, it's a point contact, meaning the surface is tangential to the cylinder, right? So the contact is just one single point. And the support reaction will be applied at or through this contact point, and it's perpendicular to the smooth surface, which means it's going up in this direction, and we usually call this normal force N, or we use N for the normal force, and it's perpendicular to the smooth contact surface. So in addition to this normal force N, if you're going to draw the free body diagram, we need to find all of the external forces exerted on this cylinder, or maybe we can simplify this cylinder into a particle. So the cylinder is also subjected to its own weight. So if it's specified, or if the weight is given, if it didn't say the weight can be ignored, then pretty much we need to include the weight of the cylinder in the free body diagram as well. And there is a cable which will pull on the cylinder through the center of the cylinder, and this force is expressed as T. So now we can see there are three external forces exerted on this cylinder. The normal force exerted by the contacting surface and the weight of the cylinder, then the force tension exerted by this cable. Since these three forces are concurrent, which means they pass through the same point, which is the center of the cylinder, then we can apply the equation of equilibrium to this particle. Or we can choose the center of the cylinder as the particle to draw the free body diagram.